Thanks for coming. This is joint work with Trevor and Lucia. So first I'm going to give an introduction about the problem of emotion analysis and why you should try to make this, to model this problem as a multitask problem. Then I'm going to give more details about the model we use in this work, which is based on Gaussian process regression. I'm going to show some, after that, I'm going to show some experiments and discuss the results and give some conclusions and directions for future work. So the goal of emotion analysis is to automatically detect emotions in a text. So for example, here we have a set of news headlines and a set of 3 emotions. And these emotions were annotated by humans usually. And you can see that it's a fine-grained task. We have like a score that ranges, in this case, from 0 to 100. And because it is fine-grained, and also because you have like usually multiple emotions, we want to tackle this problem as a multitask regression. So one of the reasons for that is because we have reasons to believe that these emotions interact between them in some way. So we want to learn a model that that we can interpret these interactions and possible correlations. But also because usually data sets are scarce and small, so these multitask models are able to make the most of these data sets by taking advantage of statistical strength from other tasks. And finally, the annotation scheme is subjective and fine-grained, make it quite prone to bias and noise. And because this is a sentiment analysis session, just a disclaimer, we're not talking about features in this work, at least at the moment. So we're going to focus only on the models. So most multitask models we use in NLP, they assume some degree of correlation between the tasks. So for example, in domain adaptation, we assume there is like some kind of general knowledge, and then we have some domain-specific knowledge that deviates from this general knowledge. If in annotation noise modeling, the setting is similar. So we have like a ground truth annotation, and we assume that the actual annotations are noisy deviations from this ground truth. But in the case of emotion analysis, we need a multitask model that is able to take into account positive correlations, but also anti-correlations. So for example, you can see that there is some degree of positive correlation between fear and sadness, but we also want to take into account that joy has an anti-correlation with the other 2 emotions. So I'm going to go like really quickly to Gaussian processes regression. You can look at the paper for more details. So we suppose that we have like a latent function that explains the relation between your inputs x and your labels y. So we assume that this function have distributed according to a Gaussian process, which is a Gaussian distribution over functions. So we have like a mean function, which is usually we assume to be the 0 constant, and we have a kernel function which gives the covariance between inputs. Okay, thank you very much. Shall we wait?
We apologize for any inconvenience.
You'll be given an extra minute.
There is no need to evacuate. We apologize for any inconvenience.
Okay, so the Gaussian process has a mean function and a kernel function. So this gives us a prior over this latent function. And we kind of push this prior through a likelihood and using the Bayes theorem. And the likelihood is where we take the labels into account. Then we normalize with the marginal, and you get a posterior for our latent function. And to make predictions, we combine this posterior with the likelihood, now with respect to our test input. And then, because this is a Bayesian model, we integrate over all possible latent functions. And in the end, what we have as prediction is a distribution. So for this work, we use the mean value of this distribution for our prediction label, but other possible decisions are available depending on the task. So in this setting, which is a regression setting, we consider a Gaussian likelihood. And the main reason why we do that is because everything here turns into a Gaussian distribution, so all the formulas, the integrals here, they become analytically available. So we have a closed form solution for all this. And so we don't need any kind of approximations. And the kernel, there are many options available for kernels, and we're going to use the radial basis function kernel, which is kind of standard kernel for Gaussian process modeling. And it basically assumes that your function is smooth. So this is for like single label. For a multitask model, we're going to extend this GP to use a vector valued function instead. So there are many ways to do this. The one we use in this work is called the intrinsic co-regionalization model, or ICM. So what we do in this model is we basically extend the kernel. So now instead of having the kernel just between inputs, you have between these input pairs, which is like input X, and D, which is the corresponding task for X. And to calculate this new kernel, we use the same like kernel for the input, and then we multiply this by a covariance between the tasks we take into account, which are encoded in this matrix. And the nice thing about this formulation is that we will be able to learn this matrix by optimizing the marginal likelihood. So in this work, to learn this matrix, we parameterize it doing probabilistic PCA. So we have like this formulation with the matrix U, lambda, U transpose plus this vector alpha. But to ensure that we have numerical stability doing the computations, we actually restate this in a different way using the incomplete Cholesky decomposition. And in the end, you have this formulation of a matrix L transpose plus diagonal vector alpha. So just to show you like visually. So we have this vector L, we compute the outer product between them, sum the vector, the diagonal matrix, and you get like something like this. And you want something that is able to make like these clusters that show like correlated tasks, but also like each column is a task here. So you want like some clusters like of correlated tasks, but also we want some of the tasks to be anti-correlated. So these would be like negative numbers, negative comparisons here. And we can, so this setting has 12 hyperparameters. So the vector alpha and this matrix L. So we can actually increase the size of this matrix L, and by increasing the size, we effectively increase the rank of this matrix B. And by increasing the rank here, we get better model capacity, so we can model these covariances more accurately. But on the other hand, we raise the number of hyperparameters, and because the marginal likelihood is usually not convex, we might run into local optima problems here. So in this work, we basically test a range of ranks and evaluate them empirically. Okay, so our experimental setup is we use the SemEval 2007 dataset, which is composed of 1,000 news headlines, and each headline is annotated with 6 emotions. Our feature representation is bag of words. We do some lowercasing and lemmatization. And for evaluation metric in terms of prediction, you use the Pearson score. So first, here we show that an instance of a learned correlationalization matrix. This was trained on 100 sentences. And you can see that it's actually learning, like, clusterizing the emotions that are similar. So for example, here we have like joy and surprise are quite similar in this like small cluster. And then you have this big cluster with kind of bad emotions like fear, sadness, anger, and disgust. And we also, another nice thing about this matrix that is learning the anti-correlation. This is it is actually a covariance, but you can see that this negative covariance is learning this negative covariance because it's detecting an anti-correlation in your data set. So you can actually interpret this matrix in some sense, which is nice. So for prediction results, we use a set of baselines. So the gray ones are single task baselines, light gray is SVM, and dark gray is single task Gaussian process. The green baselines are multitask models we used it from previous work, which are not able to model negative covariance. And the blue ones are the one we propose in this model. So if you consider all the emotions, we pretty much beat the baselines. And we also, if you consider each emotion separately, we managed to beat baselines on 3 of them. But for other 3, we didn't beat the SVM baseline. So for these 3 emotions, we still beat the GP baselines, but we are not able to beat the SVM. So we did some error analysis on that. I don't have time to explain it in detail here. You can look at the paper. But it basically has to do with different label distributions. And finally, we also made some experiments on the training sets. How do these models behave when you increase the training set size? So after having 250, 300 sentences, we can see that basically the single task GP and the multitask GP have roughly the same prediction results. So this means that we're reaching, you don't have any gains with this kind of multitask model, but it can also be because we use a really shallow feature representation. So this means we probably should look for better features in the future. So just to conclude, so the model proposed here is able to learn to take into account these correlations and anti-correlations, and for small data sets, it also performs single task baselines in terms of predictions. So for future work, first we want to model more properly the label distribution using different priors and also different likelihoods. We also want to apply other kinds of multitask levels. So you can, instead of using only on each emotion as a task, we can use each annotator as a task if you have access to different annotator IDs or other kinds of metadata. And finally, we want to try with other multitask GP models that are available in the literature. So that's it. Thank you.
Time for questions. Digestion time, but we had the alarm, so we should be awake. Okay, I have a couple of, one simple question. So you say that you use the split of 1,000 and 100 and 900?
Yes.
Why not vice versa in order to learn, on the basis of more samples? Was it the standard split used in the task? Maybe I missed something, I don't know.
It was a standard split in the task that used the mechanical Turk annotations by 2008. But we also wanted to see the behavior when you increase the training set size. So we have this belief that with bigger data sets, we wouldn't give better results by using a single task or multitask in this case. So yeah, that's mainly the reason why you did this split.
Any questions? Good.
So if I understand correctly, when you're learning the correlation matrix, you're doing basically gradient descent in the marginal likelihood of the Gaussian process, right? Yes. So did you check if local optima might be a problem? I mean, you said it's not convex, so did you empirically investigate that?
Yes, empirically. In this case, we didn't get like difference in the resulting matrix. I mean, you get like some slightly different likelihood results, but in the end, the hyperparameters don't change much in this case. Mm-hmm. So we're still using like a fairly low number of parameters here, like 20, or the order of 20 something, even though our data set is quite small. So if you want to increase, to have like a model with higher number of hyperparameters, then this might start to be a problem for you. But in this case, we didn't have this problem yet. But if you want to have like better models, you're probably going to run into this problem in the future.
Okay. Mm-hmm.
More questions? I was wondering that it could be potentially interesting because of your method to learn correlation, anti-correlation, maybe in the future to apply it on text, social media text, where a figurative language has been used, for instance, irony, sarcasm, to try to see if there is a certain correlation between or anti-correlation between certain emotion that could have triggered or help to trigger maybe the ironic effect of the short text or the sarcastic. I don't know what you think about it.
I think it would depend on which label are you. If you have like labels saying that, okay, this text has irony, like a Newman say, like, oh, this has irony in this text, then yeah, it's definitely we might be able to learn this. Because the matrix is basically learned on the label distributions. But if you don't have the annotations, then
maybe on the basis of the hashtags and trying to, on top of them, annotate in terms of emotion, and then trying to learn this. If there is asking annotators to a certain number of annotators to tag with emotion, then to learn this potential correlation between a certain emotion or anti-correlation with respect to the hashtag irony, sarcasm, not whatever.
Yeah. Yeah, I think you can definitely learn that. And in this case, I think it would be more like a classification task, I guess, because you use the hashtag. But you can definitely use GPs for classification as well. You just have to change the likelihood. So yeah, you can definitely use for that as well. But we still need the annotations with all that.
Okay, time for another question. Otherwise, we'll thank the speaker.